Just trying to move out things out of the way here, make sure everything is visible. It still says the stream is offline here right now, so just trying to see what's going on. I'm going to call it by a different name, the 24th of 11. Okay, so now it says I'm live. Internet can totally see me now to stop user encoder. Okay. Okay, so we see it coming on here. Alright. Okay, the sound seems okay. Internet can totally see me now to alright. So, again, if this didn't come on before, welcome to the lecture. Okay. So, last time you were doing polynomials. And we were looking at roots of polynomials and doing problems where we could, given the factorization of a polynomial, it makes it easier to sketch, right? Because you find the roots. And you can so we had a problem like this where you find the roots, you can factorize the expression. Originally it was x cubed minus x, right? Factorize it, excuse me. And graphing is made easier because you know where the roots are, minus 1, 0, and 1. And then you can look at the surrounding polynomials. For each root you have a factor, and you look at the surrounding part and you evaluate the factor at that root. So at x equals minus 1, you get minus 2 times minus 1, which is 2. So you get 2x. So that means there's a line. It looks like a line with slope 2 going through that point. On the other one, you get factor x minus 1. X plus 1 is that factor. Get the factor x minus 1, and then the coefficient in front is evaluate the rest at x equals 1, and then you get 1 times 2, which is 2. So again, that's a slope 2. And then at x equals 0, you get 1 times minus 1, which is minus 1. So that's a bit less of a slope. So the graph looks like something like that. Okay. So the graph of x cubed minus x. And then we saw that if you have a power law which is different from 1, the multiplicity here of all the roots is 1. Multiplicities are one for all three roots. And now here they are, for x equals minus 1, multiplicity is 1. For x equals 0, multiplicity is 2 now because the power is 2. And for x equals 1, multiplicity is again 1. So now you have the situation where each graph, okay, this is true in general. Each graph near the root looks like that power law. So this will look like a quadratic. These will look like linear, close to those roots. Okay, so you can guess that this will look like what can you guess? Well, the power the coefficient in front here, the factor in front we can also write down right? If it's minus 1, then this is our this is going to be our expression for nearby the root, x equals minus 1. And then the factor in front, or the coefficient in front, let's call it the coefficient, that's a little bit better. Coefficient of the approximated function near that root is going to be, just substitute in x equals minus 1. And you get 1 minus 1 squared is plus 1, and then times minus 2 is minus 2. And in here, we take x squared and evaluate at the other rest of it at x equals 0, so we get minus 1 outside. So it becomes minus x squared. And this becomes, you take x minus 1, that's our factor, then you evaluate the rest at x equals 1, you get 1 times 2, which is 2. So here the slope is minus 2. It's going to go down like this, something like that. Here the slope is plus 2. And here it looks like a minus x squared, so it's a parabola opening downward like this. Okay, so joining all the parts, you get something like this. This keeps going. All right, so now it goes off to infinity, right? So as x goes to infinity, if you multiply this out, this is x to the 4th. So that we know, and the coefficient is 1. So x to the 4th goes to infinity, or y goes to infinity as x goes to plus infinity, and y goes to infinity as x goes to minus infinity as well. So it's, as you could guess, it's going to be a symmetric function, so it's an even function. This, by the way, is an odd function. So you check that f of x, if you plug in minus x into the function f, then you get minus the function at x. And that you can see is true because this becomes minus x, this becomes minus x plus 1, which is negative of this term, and this becomes minus x minus 1, which is the negative of this term. So the 3 minus signs and the factors will give you the same with a negative sign overall. And this will give you, same thing, the minus x will give you minus x plus 1, which is a negative of this. This will give you minus x minus 1, which is a negative of this. 2 minus signs will cancel, and meanwhile, the minus x squared here just gives you x squared. So f of x, you can check f of x, minus x is equal to f of x here. Okay, so those are 2 simple examples of using the power behavior of the factored form. The powers of the roots are known. The multiplicities of the roots are the same as the power of each linear factor. These are called binomials, by the way, because they have 2 terms, a linear term and a constant term. Sometimes I just call them linear factors, but yeah, they should be, I guess the right term is binomial. Okay, once they're factored like this, you look at the multiplicity. The multiplicity tells you the behavior of the function at the roots, and then you can fill in the gaps by, well, you have to determine also another point off the x-axis to determine what the function looks like. So say x equals 1/2. And then you get well, it's going to be kind of a mess here, but anyway. F at x equals minus 1/2 or plus 1/2 is the same thing. We get x squared is 1/4, and then this is going to be, for just take it to the x to the plus 1/2. And then the same thing will be, you'll get the same thing if you take x equals minus 1/2. So x equals plus 1/2 is 3 over 2, so it's multiplied, and then this is subtracted, you get minus 1/2. So it's negative, the overall sign is negative as you might expect, and it's minus 3 over 16. Okay, so somewhere in here, this is, it's not saying this is the minimum points, but we don't know what the minimum is. But somewhere in here you'll have a value of minus 3 over 16 for y. Okay. And we could do the same here to find a particular point, say x equals plus 1/2, then we'll get x cubed is 1/8 minus 1/2. That's going to be 1 over 8 minus 4 over 8, which is minus 3/8. So somewhere around here is going to be the value minus 3/8. I'm not saying that's the minimum. The minimum might be at another point x, but at least it's a particular value that you can write down to show the scale, the overall scale in the y direction of the graph. Okay, and we gave an example last time where you can look at the graph, at a given graph, and write down an expression for, for the whole function. And given points on the graph, then you can evaluate the overall constant in front. You first find the roots, that gives you the function with the overall constant not yet determined, a, or an. Say we do it with this one. And then you look at a point on the graph, which is different from the root values. So a point with a non-zero y value. And that determines an. So whatever the value you give it is, you can substitute that into the formula. And generally you'll get the polynomial expression in here. So, where this p of x has a leading coefficient of 1. Right now, I wanted to talk about also the intermediate value theorem. All right. So what that theorem is saying basically is that if you have a smooth function, in some sense, a nice function. So it's smooth in the sense you don't have to take your pen off the page when you draw the function. A better word perhaps would be continuous. Continuous means that you can draw the graph. You might have sharp corners. It has to be a function, but you you can draw it without taking your pen off the page, something like that. So with such a function, you might have, let's look at a region where the function passes from negative values of y to positive values of y. Okay, so you have an a1 here and an a2 here. So x is equal to a1. When x is equal to a1, y is defined as, let's say, the function f of x. So it's f of a1. That's the value of y there. So I write both as an ordered pair just to show the coordinates of each point. a2 and f of a2. Okay. So the intermediate value theorem tells us that if the function is continuous on this interval between a1 and a2, between the interval a1 a2, then if you have a change in sign of the y value, so if f of a1 is less than 0 and f of a2 is greater than 0, then the function must be 0 at some point between a1 and a2. For some value of x, call it c, basically f of c is 0. So if f of a1 is less than 0 and f of a2 is greater than 0, then there exists a c, a value of c for x, so an x value of c, where a1 is less than or equal to c. Actually, c is strictly greater than a1 and strictly less than a2. Of course, because if c ever equal to a1, then f a1 would have to be 0, and that's not true. Or if c is equal to a2, then f of a2 would have to be 0. So there exists such that f of c is 0. Okay, so this is a mouthful of mathematical terminology here. If f of x is continuous on the interval a1, a2, and if f of a1 is less than 0 and f of a2 is greater than 0, then there exists an x value of, call it c, where a1 is less than c is less than a2, so c is between a1 and a2 within that interval, such that f of c is 0. So it's just, you can't take your pen off the page, so somehow the y values will be continuous as I draw the line from here to here, no matter what the shape is. I might hit 0 early and then reach this. I might go way up and then down again. I might go way down and then up again and reach 0 only near the end of that interval, but somewhere there it has to go through. There's just no way you can draw the line from here to here without hitting continuously and draw it like it should be a function. Just draw it in a functional way as it should be. Okay, so it might cross twice or 3 times, or 5 times I should say. 1, 2, not 2 times, but 1, 2, 3. It has to cross an odd number of times if it crosses more than once. So there's all sorts of behaviors you can have, right? But it has to hit somewhere in between, at least one place. So all we know is there's at least one c, such that f of c is 0. Okay, so this is helpful. This is helpful for finding roots of polynomials where you might have real coefficients which where the root cannot be expressed as a simple rational number or integer or something. So let's check to see how this works. So confirm, so example, confirm that there is a root between 1 and 3. There is a root of the function f of x is equal to x cubed minus 4x between 1 and 3. Okay, so I wrote down a simple case. Now in this case, we can actually factor that. So factoring it, you get x squared minus 4 times x, and that factors to x plus 2, and x minus 2. So in fact there are 3 roots, one at x equals minus 2, one at x equals 0, and one at x plus 2. So we know there should be a root between 1 and 3. And likewise between minus 3 and minus 1, and so we can check those as well. Also between minus 1 and 1. Okay, so let's check the 1, 3 interval first. Let's call them A, B, and C. Okay, so you simply evaluate the function at the 2 endpoints of this interval at x equals 1. Okay, so you'll get 1 minus 4, which is minus 3. At x equals 3, you get f of 3, which is 3 cubed minus 4 times 3, which is, so the first is 27, minus 12, so it's plus 50. So you do have one number is negative, and the other is positive. I forgot to mention in that theorem you could also have it going the other way. You could have f of a1 could be, or in that previous theorem, f of a1 could be less than 0 and, sorry, it could be greater than 0 and f of a2 less than 0. So it could be doing this kind of thing instead. Oops. Okay, this function could look like this, and then there would be an interval a1, a2 here, and there would be the c between a1 and a2, for which the function is 0, or we sometimes say vanishes. So fc equals 0. That's the same as saying f of x vanishes at x equals c. Again, sort of mathematical lingo or terminology which we use often. Or f of x is simply a root at x equals c. That's another way of saying it. Okay, so So here we have a change of sign, and that shows that therefore there must be a root between 1 and 3. So C must be bigger than 1, less than 3, and f of C must be, so therefore there is a C such that 1 is less than C less than 3, and such that f of C is equal to 0. Okay, so just writing it all out. And B, so minus 3 minus 1, f of minus 3, so it should just be the negative of what we had here because it's an odd function. And so we get minus 27, right, in the original one, plus 12, so we do get minus 15. And then f of minus 1 is minus 1 plus 4. Again, that's the negative of the value that we got here, plus 3. So again, this is less than 0, this is greater than 0. And so that there is a root between those two as well. So we'll just write it a different way. Root of f of x exists in the interval and we'll make it now rounded brackets minus 3 minus 1. Since we know the root cannot be at the endpoints. Okay. And finally, the third one, we already have the values for f equals f of minus 1. That's going to be plus 3, and f1 is minus 3. So again, this is greater than 0, and this is less than 0. So as long as there's a change in sign from one side to the other, it doesn't matter if it's going from negative to positive or positive to negative. This will be the latter case. That will give us a root between minus 1 and 1. Okay. So in particular, that root would be 0. And this root would be 2, this root would be 0. Oh, sorry, this is 2, this is minus 2, and this is 0. Okay. Now let's do some other examples of exercises at the back of the book there that are interesting or helpful for understanding this material better. Okay, so I chose 57, number 57 in section 5.3 exercises. Okay, so that's saying you're supposed to write down the formula given the information here. So you have degree 3 polynomial, zeros at x equals minus 2, 1, and 3. Y-intercept is at 0 minus 4. Okay. So this is just describing, first of all, where the roots are, what the degree is, and where the roots are, and then where the y-intercept is. So from all this information, we can determine the precise formula for the whole polynomial. Okay, so if it's degree 3, first of all, then you can have at most 3 roots. Some might be repeated, but we're given 3 different roots. So therefore, 3 different roots tells us that each root must have multiplicity 1. So the 3 distinct roots have degree 3 implies, that's my symbol for implies, that each root must be multiplicity 1. Alright? So we have the following function, f of x. So there's some overall factor a, which is not yet determined. And I write down the root factors corresponding to each root. So x plus 2, that's going to give me a root at x equals minus 2. X minus 1, that's going to give me a root at 1. And x minus 3, that's going to give me the root at, when I plug in x equals 3. Okay, so I have the entire form of the expression right now already, except for a. And there's only one piece of information left, namely the y-intercept is at 0 minus 4. And that last bit of information will help me determine a. So use the y-intercept is at x equals 0, y equals minus 4. Okay, so all I have to do is plug in x equals 0 into this expression. It doesn't affect this constant a. Right, this is just some constant not equal to 0. Right? Otherwise the whole thing is 0. And it's not going to be a degree 3 polynomial anymore. Alright, so you put in x equals 0 and you get f of 0 is equal to, which is y. So it should be minus 4. And on the other side, you get a, and then you plug in zeros for each expression. You get 2, minus 1, and minus 3. And so this product multiplies out to give you 6 times a. So a, when you solve it, you get minus 4 over 6, which is minus 2 over 3. Okay, so that gives you the whole polynomial expression, which I can multiply out if I so wish. I can multiply this out and eliminate all the brackets, if I wish. Okay, so that would be the answer for number 57. Okay, so number 66 is a similar example, except there's a double 0. That means you have a 0 of multiplicity 2 at one of the points. Okay, so you're given here a double zero at x equals -3 and a triple zero so we actually have a double zero at one point and a triple zero at the other point. Triple zero at x equals 0. And it passes through (132). Point when x equals 1, y is 32. Okay, so now we're told explicitly what the roots are. We have a root at 0, we have a root at -3. Okay. And here we have a triple zero at this root and a double zero at that point x. Okay, so now we can just simply write down the whole expression except for the leading term, or the leading factor. So we have a leading factor, and now the double zero will be the factor that gives you that 0, that x, that value of x will be 0 when you have the factor x plus 3. Oh, sorry. Yeah, this factor will become 0 when x equals -3. So that will give you a root of, that means x minus 3 is a root of this polynomial function. But you have to remember there's a double zero, so that means there's a power of 2 there. Now the factor I have to write down here to give me a 0 at x equals 0 is simply x. And it's a triple zero, so that means it's x to the power 3. Okay, so you see how simple this is, but don't be confused that this is a 0 when x equals 0. That just means there's no linear term in this factor here. So it's a simple power law here. Okay, the 0 here means x. That's the location of that 0. Doesn't always mean that that's the 0 of the whole polynomial, unless you're told that. Okay, so now, in other words, this is a special case, not to confuse anybody, but it's a special case where x equals 0 and y equals 0. Okay, so it makes it a 0, and it's actually an x-intercept and a y-intercept at the same time. Okay, so the y-intercept is 0 here. All right, so use the last bit of information like I did before. When you plug in x equals 1, what do you get? Should get 32, but on the in this expression, I get a, plugging in the value 1 for each, wherever I see an x here. Okay, so this becomes 4 squared, which is 16. This is 1 cubed, which is 1. So I get a times 16 times 1, so 16a. And now if that's 32, then I have an equation I can solve for a. 16, I can divide 32 over 16, and I get 2. So x equals 2 is the factor in front. So I write it all out. X equals 2x cubed. I can put that factor first. X plus 3 squared. Okay. So this is our final form for that exercise, the final answer for that function that you're asked to find for number 66. Okay, so the next section I want to go on to is 5.4, dividing polynomials. All right. So you remember in division, say 26 divided by 5. How do we do that? Well, we have long division. So I'll just review simple long division for you. And this is very much like what we'll do when we divide polynomials. So if you have two integers and two whole numbers, or two natural numbers, the second one not being 0, then you can divide first by the second. And we do that using long division in this way. So we strip away all the signs. So we just get positives and then put in an overall positive or negative sign later as we need it, according to whether both are positive or negative, or one is positive, the other is negative. Right, so you know how to do that. The overall sign is going to be positive if both sides are the same, and negative if they're different. So if we look at how many factors of 5 go into 26, then we know there are 5. We find the maximum number without going over. 5 times 5 is 25. And then we subtract and we get a remainder of 1. Okay, so we can write this as 26 over 5 is 5 plus the remainder divided by, this is the divisor, this is the dividend. The whole thing is called a quotient. Okay, so you remember those terms. Quotient is a ratio. The dividend is 26. The divisor is 5. The remainder is 1. Okay, so the quotient without a remainder is going to be 5. I think oftentimes people, okay, quotient generally speaking means this ratio, but in this case when you're dividing one by the other and you're breaking it up into the different parts, you have what's called a quotient, that's without the remainder, and then the remainder. And the two together make, you should probably call this the ratio then. The entire ratio, or one polynomial divided by the other. Okay, so let's see how this works with polynomials. So with a polynomial, you look for, you arrange the two polynomials. So let's see an example for polynomials. You arrange these polynomials in decreasing order. So divide 16x cubed minus 12x squared plus 20x minus 3 by 4x plus 5. Okay, so we want to write it in decreasing order in powers of x, which it already is. It's already in that order. The first one is. And the second one is also. And, okay, so we put it under this root divisor sign. You put the dividend in there. Usually it's the bigger polynomial. And you divide by the smaller one. So f4x plus 5 goes in here. So very similar to what I've done up here. And then you look at, so you make sure that, okay, all the terms are put together, so you have a single term for each power of x. Okay, if you don't, then you should just combine like terms. And then you'll get one coefficient for each power of x. And now I'll do this one term at a time. So I'll look at the first term of the polynomial here, and I'll see how many times does it go into, divide into this term here, the first term of the bigger polynomial. How many times does it go in? Well, you just take this one and divide by this one. So 16x cubed over 4x, you just divide, and these factors will cancel except for an x squared up in the top, and this will cancel, give me 4. Reduced to 4x squared. So that's going to give us, that's what I put up here. So that's just like dividing 5 and looking for the maximum number of powers of 5 that, okay, the second power, or the maximum multiples of 5 that will go in there without going over. Okay, so here you look at the first term and then determine this number, which when multiplied by that first monomial means one term. It'll give you the leading term or the leading monomial of this larger polynomial. Okay, so just monomial. Let's write out that term, monomial. So it's one term in a polynomial. Right? Binomial means two terms. So a two-term polynomial. And a trinomial, etc. Okay, so that's just some terminology which hopefully is a review. You've seen this before in Math 101 or 099. Okay, so let's give ourselves some room. Now, when I multiply this, I'm going to multiply 5 times 5 is equal to 25. It's going to be like that, but here I multiply this as starting factor with this whole thing here. So the first term will give me just 16x cubed. So it should be the same as before, because that's how I determined 4x squared. But I have a second term which is plus 20x squared. So I multiply 4x squared by 4x and then by 5. So I just use the distributive law to get both of these terms. And then I subtract. So what will happen is this term will cancel this, so I subtract here. And I'll get 0 here, and here I'll get minus 12 minus 20, which is minus 32 x squared. All right? So then I'll just bring down the remaining terms here. So this is like a remainder so far. Right? So now let's say we had a decimal here. 0.5, and so then our process will have we'll need to continue. We haven't finished it. So we have to bring down a 5, and then I'll divide 5 into 15, I'll get 3. That's the remainder, right? So we'll continue this whole thing, and now the remainder gives me 0. So 5 times 5.3 should give me 26.5. Okay, so in this case, again, we continue the process. 4x into the leading term is what? So you divide the leading term here by 4x. So 32x squared minus 32x squared divided by 4x. You get 8 minus 8x. So that's what you put in here. Now minus 8x times this whole 4x plus 5 is minus 32x squared. And then minus 40x. Subtract. So this will cancel now. I'll get 0. Here I'll get minus plus 60x because I have 20x minus negative 40x. Okay, so watch the signs. So sometimes you can do that just by canceling here, here, and here to cancel all the signs in each term. Or change the sign. If it's positive, it should become negative. So this will become, in this case, positive. This will be negative, and this will become negative. And then you add. So adding gives you 60, and you have minus 3 left over. So finally, 4 into 60 goes 15 times, so you get a plus 15. And so that gives you 60x plus 5 times 70. 5 times 15 is 75. And then you subtract that, so this becomes positive, this becomes negative, negative. And then add, and you minus 7, you get minus 78 here. Okay, so the minus 78, you can write that at the end there as the remainder over the divisor. Okay, so all that together means that putting it all together, x cubed minus 12x squared plus 20x minus 3 divided by 4x plus 5 is equal to 4x squared minus 8x plus 15 minus 78 over 4x plus 5. Okay, so that's what we've gotten so far. So this should be the answer, but really, is it the answer? How would we check this in a simple way without doing exactly the same thing as we did before to find the answer? Well, it's just like when we write 26 over 5 is 5 plus 1 over 5. How do we check that? Well, we say, we just go backwards. We say, well, is 5 times all of this equal to 26? So you take 5 times 5 and add the 1. 5 times 5 is 25, plus 1 is 26. And then that tells you that you did get it right in the first place, right? So check. Take the quotient times the divisor, and then add in the remainder, and you should get back the original dividend, or the original number in the numerator. So ratio is the numerator, that's a denominator. So I do the same thing here. I take 4x plus 5 times this, and multiply it all out. And add in the remainder, which is minus 75, minus 78. And then I see, is that going to be equal to the original thing? So I go ahead, and 4x times 4x squared is 16x cubed, minus 32x squared plus 20 x squared. Okay, so I can, I'll do it separately just to make it a little more clear, but I could actually do that in my head. And that's minus 12 x squared, which corresponds so far to the answer. Then I look at the x term, and I get plus, so the three terms which, or the two terms which I look at are these two. So 60x and minus 40x. And then finally, 5 times 15 is plus 75. And then I subtract minus 78, the final term. And so I see that these are all the same terms. Okay. So that constitutes a check, a useful check for this. So I'm sure this is the correct answer. Okay. Now let's look at another way of doing these division problems, and that's using so-called synthetic division. Synthetic division is simply a way of writing down the coefficients without writing the powers of x anywhere. Okay, but we have to be a bit careful and watch for zeros in case there are any. There might be coefficients which are 0. We have to watch for those. Okay, so let's try a simple example here of synthetic division. So I'll do one of these exercises. This is exercise 3 at the end of section 5.4. This, by the way, was number 16 in section 5.4 exercises. So here you divide, number 3 is what we're doing, is x squared plus 5x minus 1 divided by x minus 1. Okay, so here's how you do synthetic division. You write down the coefficients only of the three different terms of the first bigger polynomial. So you write it in a row like this. 1 is the first coefficient, 5 is the second coefficient, and minus 1 is the third coefficient. Okay, and you can leave a little bit of room here for the answer. Now what you do is, here you have to have a simple root with a binomial factor here. You just have to have, you'll have to have two terms here, and the leading coefficient should be 1 for this one. Okay, and what you put down now is you put down the root that you would get from this factor. The root is 1. X equals 1 makes this factor vanish. So that's actually what you put down, 1, not minus 1. So it's just the opposite sign of this constant term here of that binomial. Now what you do is you you start with 1, so you just bring down this coefficient 1. If this coefficient is 2 or 3 or something higher, that's what you put down here. So, but in the first step, you just bring that down, it becomes the same thing. So nothing changes there. Now what you do is you take this factor and you multiply it by this one and add it to this one. Okay, so if I do that, 1 times 1 is 1, plus 5 is 6. And then I do the same thing. Take this function x, or so this value of x, that makes this whole thing 0. And I multiply by this and add it to this. So 1 times 6 is 6, minus 1 is 5. Okay, so what this tells me so the operations that I have done here are just like what I would do if I took this polynomial and divided by this one in the way I did before. Okay, if you look at how I do this before, you would take x minus 1 and divide it into x squared plus 5x minus 1. So this divided by this gives me 1x, right? X squared minus x would give me this. And then subtracting, I get 5 minus 1, which is 6x. All right, so what I've done here is I've multiplied this factor by, so first I bring down a 1. Okay, that will correspond to the coefficient in front of this, actually. And then I take 1 times this 1 and add it to the 5. And that's essentially what I'm doing here, because I'm taking a minus 1 and then I'm subtracting that minus 1 from the previous thing. So the minus signs will cancel and I'm adding, actually, the 1. So I take 1 times 1, which gives me x, and then I'm adding x to 5x, and I get 6x. So the next coefficient will be 6 that I have to try, and then that will give me 6x. So I get a minus 1 up here and a 6x minus 6, and when I subtract, these are both subtractions, I get plus 5. So again, I take the 1 times the 6 minus 1, and that gives me 5. So 5 will be the remainder, and the 1 and the 6 will be the coefficients of the polynomial in what I called the quotient earlier. Okay, so you could just basically read off the remainder. It's going to be 5, and then you can also read off the quotient. It's x plus 6, and the remainder 5. And remember, as before, I can check to see if this works by going back and multiplying x plus 6 by x equals x minus 1, x plus 6 times x minus 1, and then adding 5 and seeing if that gives me the original polynomial. And I get x squared plus 6 minus 1 is plus 5x minus 6 plus 5, which is indeed x squared plus 5x minus 1. Okay, right here. Okay, so this is the idea then. You represent a polynomial by its coefficients. You write those coefficients in decreasing order in powers of x. You only write one factor outside that, and then you evaluate as I showed you until you get an answer in the final column. And that will be the remainder, and the previous numbers will be the coefficients of the polynomial of the quotient. So another example, number 14, is to divide 3x cubed minus 2x squared plus x minus 4 by x plus 3. So again, 3x cubed minus 2x squared plus x minus 4 divided by x plus 3. Okay, so again, I can so I'll have a 3, the leading coefficient is 3, and then I have a minus 2, 1, and minus 4. So you have to be careful here, because if there's a missing power of x, so if I didn't have this x squared term, then I would just have 3x cubed plus x minus 4. Then I would have to put a 0 in this column here. That's highly important when you're doing this division. Okay. So now I do this synthetic division by starting with a minus 3 over here. I can draw these lines and make it into a table. Okay, so minus 3, I start with 3 here. So minus 3 times 3 is minus 9. Minus 2 is minus 11. Minus 3 times minus 11 is plus 33. Plus 1 is 34. And then finally, minus 3 times 34. You can do this by hand if necessary here. 3 times 4 is 2. 3 times 3 is 9. Plus 12. Or plus 1 is 10. So it's minus 102. And then minus 4 is minus 106. Okay, so this is our final remainder, the answer for the remainder, and these will be the coefficients of the polynomial that I get when I divide this by this. So this quotient polynomial, whose coefficients are this, will always be, in this case, of degree less of degree that's 1 less than the original degree. Right, since I'm dividing by x plus 3, the monomial, or a binomial here, which is just a linear expression. So any time you divide degree 2 by a degree 1 polynomial, or degree n, and then by degree m, you'll get final one will have a quotient of m minus n, or n minus m. So if the polynomial, let's try it. Let's use different terminology here. So f divided by g. So if this has degree n, and this has degree m, then you'll have a quotient polynomial which is degree m. So we can see that right away here, that this final one will have degree 0. This remainder will always be degree 0, which is 1 less than the degree of this, which is 1. Okay, so that's how we do division of polynomials. Yeah, I should write this out. This is equal to then quotient is 3. We have 3 of them, so this will be the constant term. This will be linear. This will be quadratic. So 3x squared minus 11x plus 34, and the remainder is minus 106. And we could always check that out by multiplying it out backwards and seeing if you get back the original dividend. the original number, the original numerator. It's not a number, it's a polynomial here. All right. So now let's look at this expression here. This expression is equivalent to, if you multiply both sides by g of x, so it's multiply by g of x on both sides. Okay, then I use a distributive law and I get g of x times q of x plus, and the g's will cancel and I get r of x. Okay, so it's just what I was saying before. This is a way of checking my answer. If I take the quotient, multiply by the denominator, and add the remainder, then do I get back the original numerator? But now this is an important way of writing it, because if r is 0, okay, so if the remainder polynomial, which in this case is a constant polynomial, so I can actually replace this by just r. If r is 0, then yeah, let's use big R here, because that's a little bit. I want to use little r for root, and big R means remainder. So if the remainder is 0, then what I can see is that I've factorized my polynomial into two smaller polynomials. Okay, so I can say that f is divisible by g of x. Or g of x is a factor of the original polynomial. F of x is divisible by g of x. Or I could say f of x is divisible by q of x, by the symmetry, if I want as well. In which case, q of x is also a factor of f of x. So a factor remaining if I divide f of x by g of x. Okay? So one of the problems is to determine if one polynomial is a factor of another. So the question here is x minus 2 a factor of 4x to the fourth minus 15x squared minus 4? Is x minus 2 a factor of 4x to the 4 minus 15x squared minus 4? Okay, so one way to do it is simply to divide this by this. And I can use synthetic division to do that. So now, just to illustrate the things you have to be aware of. My first coefficient will be 4. My second one will be not minus 15, but 0, because I should have an x cubed term here normally, but its coefficient happens to be 0. So I have to put a 0 there, and then I get minus 15 for the x squared. And then the x term also gives me a 0, and then I get minus 4 here. So I have these two zeros that I have to insert at the appropriate places, corresponding to x cubed and x. And then I take my 2, put it out front, and then I go ahead and do the process here. So 4 times 2 is 8, plus 0 is 8, 2 times 8 is 16. Minus 15 is 1. 2 times 1 is 2 plus 0 is 2. 2 times 2 is 4. Minus 4 is 0. Okay, so that means the remainder is 0. All right. And so I can say, yes, this is a factor of x minus 2 is a factor of this. What is the quotient in this case? The quotient here will be given by these coefficients, which I have to start with x cubed now, so it's 4x cubed plus 8x plus, x squared plus 1x plus 2. So I should have all the coefficients then for all of the terms starting from the x cubed term all the way down to the constant term. So check it. Well, just substitute, multiply it all out again. Just go backwards and multiply it out, and see if the original expression is obtained. X times 4x cubed is 4x to the 4th, plus 8x cubed minus 8x cubed is 0. So that cancels. X squared minus 16x squared is minus 15x squared. Plus 2x minus 2x is 0 again. I'm going to write it out explicitly there. And then finally minus 2 times plus 2 is minus 4. So these will go away, and I do get the original expression, so because I don't usually write those. Okay. All right, so I've gone a bit long again. So we'll continue with finishing off this section for 5.4 next time, and I'll give you some update as to when the quiz will be as well shortly, and as well as getting back your homework. I'll be working on that as well. Okay, so have a good day. Hudofes. Shabbat Chush.